So my name is Juliette Rooney-Varga, and I'm Associate Professor and Director of the Climate Change Initiative at the University of Massachusetts in Lowell. And today I'm excited to talk to you about climate change, biology, and using a systems thinking lens to look at climate change. So in this talk, I'd like to start off by giving a brief introduction to how climate change intersects with biology, and then take a tour of some of the basic, well-understood facts about climate change. As I mentioned, we'll also show how tools from systems thinking can help us make sense of complex, dynamic systems in a way that's very relevant for understanding climate change, and also how it affects biological systems and how we might address climate change. I want to start off by making it clear what we're talking about when we're addressing climate change. So there's weather and climate, and often people get the two mixed up. So just to be completely clear, weather refers to atmospheric conditions such as temperature, relative humidity, light, wind, and other atmospheric factors at a given time and place. That's different from climate, which is really the long-term average weather that occurs in a particular region. Typically, we're talking about long-term being something like the average conditions over a few decades, like 30 years. So here we're talking about changes in climate, not necessarily changes in these short-term weather conditions. And you might not think of biology and climate change as being closely linked, but they are. Climate change impacts pretty much every type of biological activity. And I guess we know that by how obsessed we are by the weather ourselves, right? It affects human physiology, it affects what we're able to do, but it affects the physiology of plants, animals, microbes, pretty much any type of biological activity. And at the same time, biological activity affects the climate. So we have the biosphere as a major driver of the carbon cycle being critical for climate change, and also of other properties like albedo and other greenhouse gases, such as methane and nitrous oxide, and many others. So these two are really intertwined and very relevant for each other. You may also not think of yourself as having a career that's going to be impacted by climate change if you're interested in biology, but I think you'll find that increasingly biological careers and climate change will be intertwined and already are. So some examples would be biotechnology, the use of biotechnology to develop new biofuels, for example, or ways to sequester carbon dioxide and other greenhouse gases from the atmosphere. Drug discovery. Increasingly, pharmaceutical companies are interested in what are the drugs that we're going to need in the future. And many of those will be determined by the expansion or change in the geographic distribution of diseases that are influenced by climate change, like malaria, dengue fever, yellow fever, and others. Public health and medicine, increasingly impacted by climate change and relevant to climate change. Many of the first responders in natural disasters are people who are dealing with health problems. And also much of our public health is influenced by climate. So for example, asthma rates influenced by heat, relative humidity, and pollutants sort of in cities especially. If you're interested in ecology, I think it's kind of a no-brainer that climate change is relevant, as the distribution and behavior and activities of organisms in the environment are so controlled and so driven by temperature, moisture, and other factors related to climate. Same thing with conservation biology. How will we manage to preserve organisms, preserve species, manage our natural spaces in the light of a changing climate? And also, how will we adapt our agricultural systems to not only deal with changing climatic conditions, but also to perhaps be part of the solution to reducing greenhouse gas emissions and making our systems more resilient to a changing climate? Okay, and I also mentioned systems thinking. What do we mean by systems thinking? Here, what we're really referring to is a framework or a perspective that examines the whole system, rather than being analytical and focusing only on the elements of a system in isolation, which would be more like a reductionist approach. So with something as complex and dynamic as climate change and the human systems that interact with it, it's really helpful to take a systems perspective. And there are some basic concepts in systems thinking that can help us understand those complex dynamic systems. Okay, here I want to start off with thinking about the atmosphere. And if you're like me, you may enjoy, on a sunny day, walking outside, looking up at the sky, and thinking about a vast open space. From our vantage point here on Earth's surface, the atmosphere seems like a vast open space. But in fact, it's not. About 90% of the molecules in Earth's atmosphere are in a thin layer that only reaches about 12 kilometers or 7 miles above Earth's surface. Just to scale, that's roughly the same in thickness as the thickness of an apple skin if the apple were the Earth. So it's this very thin layer. Here's a visualization that shows that. So this is a visualization of the volume of Earth's atmosphere relative to the Earth's volume. So that wouldn't matter, except that we are using fossil fuels such as coal, oil, and natural gas, which when the carbon-carbon and carbon-hydrogen bonds in those fossil fuels are oxidized or combusted, they form carbon dioxide. And carbon dioxide has been known for a very long time to trap heat. It's a greenhouse gas, the most important greenhouse gas that that is driving the climate system currently. So for over 200 years, carbon dioxide has been known to trap heat. Okay, so that wouldn't be a problem except for the scale of emissions. So here we've got the average American emitting about 20 tons of carbon dioxide per year. That translates roughly to about 100 pounds per day. Collectively, all human activities currently release about 37 billion tons of carbon dioxide per year. So one way to visualize that would be to take the coal in the hoppers that you see in that train and all the carbon that's represented by that coal, transfer that to the atmosphere, and in order to make up 37 billion tons of carbon dioxide per year, you would need a train that wrapped around Earth's equator about 54 times every year. So that carbon dioxide from both fossil fuel use, and in the bottom what you see is 3.3 billion tons of carbon dioxide per year as a result of land use and deforestation, goes into the atmosphere, but some of that, about 50% of it remains in the atmosphere, and the other 50% is taken up either by land plants. You see the 26% represented by the terrestrial sink or land plants, and 24% is currently taken up by the oceans, primarily through abiotic diffusion. So together, the land plant sink and the ocean sink represent what we call net removals from the atmosphere. Okay? So we've got emissions into the atmosphere and then flow or removals out of the atmosphere. And indeed, if we look over time at the atmospheric concentration of carbon dioxide, this graph goes back about 800,000 years using ice core data, and then in the latter part of the graph looking at actual observations of the atmosphere. And so what you see there is right up to the point of basically human agriculture being invented. You've got carbon dioxide concentrations varying between glacial and interglacial periods between about 180 and 280 parts per million, but really staying within that band. Then we've got human civilization kind of coming online, that stable period. And then since that time, since the start of the Industrial Revolution, a quite dramatic increase of about 40% to, in 2014, 400 parts per million carbon dioxide. Now we've got, looking out into the future, what I see as our choice. So in one scenario is a low emission scenario, which would put us at about 450 parts per million. And another scenario, which is actually the track that we're basically on currently, would be a high emission scenario, which would put us well over 800, closer to 900 parts per million by 2100. So that's really what the choice is looking out into the future. Okay, so how do we get there? Let's just say that our goal is to stabilize atmospheric CO2 at around 450 parts per million. What will we need to do to emissions in order to achieve that goal? So here's a graph of emissions from 2000 to 2100, and here are some choices. The first choice is A, a shape that looks pretty much similar to the shape that you just saw, stabilizing emissions. Another choice would be B, decreasing emissions after a while with a fairly moderate decrease. And the last choice would be C. So if you could just take a moment and think about which one of these choices you think is appropriate if we want to stabilize carbon dioxide concentrations at 450, that would be great. And if you could even write it down, A, B, or C, that would be even better. So if you've committed to your answer, and I'm just showing you a reminder of what the concentration pathway looks like, most people give the answer A. So I don't know if you fell in that category or not, but if you did, you were in good company. A lot of very well-educated people have given that answer. The correct answer is actually C. And that's clearly a very dramatic decrease in emissions in order to achieve a stabilization in concentration. Why is that? And I'm just going to give a really simple example. Here's my water jar. And we can think about the jar as the atmosphere, a finite volume. And if I had another jar and I was pouring emissions into that atmosphere, the jar of water is filling up, right? So in order to stabilize the concentration, essentially, I need to stop pouring into the jar. And that's the same thing with emissions and concentration. Here's one more choice. Let's say that we decide to put off action and choose a later date to start reducing emissions. Because it's still the same jar, and it's still got the sort of memory of emissions from previous times. If we still have the same stabilization goal, that means that we actually need to reduce emissions even faster, be on a steeper rate of decline in order to meet that same goal, because we've taken up some of the space in the jar by emissions that have already happened. So this brings up a key system concept of accumulation as a result of flows into and out of stocks. So here we've got a simple system with a stock, anything that can accumulate or decline, and a flow into that stock, an inflow, as well as a flow out of the stock. And just like my jar of water that either I pour into or drink out of, or I do both, or the atmosphere where we've got emissions and net removals, anytime where we've got an inflow which is greater than the outflow, the stock will accumulate. So here in the case of atmospheric CO2, if emissions are greater than net removals, as they currently are, atmospheric CO2 increases over time. Okay, so this atmospheric CO2 is a greenhouse gas. It traps heat. It's been known to for a long time. And as it accumulates, it's a major driver of global temperature. And this is also, nothing that's contested. It's very solid science. We see a clear record of increase over time in global average temperature so far from 1890 to currently of about 0.85 degrees C. If we include the increase in heat content of the oceans, where actually about 90% of the heat imbalance is accumulating, you see a very clear signal over time of increase in ocean heat content, even since the 1970s. And I actually just want to point out too that the energy budget of the Earth or of the oceans can also be considered a stock and flow system. And we'll come back to that and why it matters in a bit. So you might think 0.85 degrees C, or looking out to the future, let's say 4 or 5 degrees C. What's the big deal? Why does that matter? But if you're thinking about biology, you know that for yourself especially, or for most mammals or endothermic organisms, it could matter a lot, right, if your temperature goes up. Similarly for the climate. A small shift in mean can lead to a very large shift in extremes. So here what you see is two normal distributions, one showing the previous climate, and then the other showing a shifted climate. The same distribution, but with a new mean. And what you see here is that in the old climate, there was that pink area under the curve represented an extreme heat event, like a heat wave. But if we shift the mean a little bit, then the area under the curve that's pink has grown a lot. And now you've got much more extreme heat, but you've also got a new kind of extreme heat, that red heat, which is an entirely different set of conditions than occurred previously. So you can see how a small shift in mean can lead to a large shift in extremes. And for biological systems especially, it's those extremes that matter, right? It's a few days of extreme heat that can wipe out a wheat field rather than the mean temperature of the entire summer. If we throw on top of or if we take a look at a shift in variance as well as a shift in mean, you also see extremes on both sides changing. So here we've got the same mean, but more variability. And here you see more cold weather on one side, a new kind of cold weather, and more extreme hot weather on the other side. If we combine both of those things, basically shift the mean and also broaden the variance, which is actually what climate scientists expect to see in the future and what we've already witnessed a little bit of so far, then we actually see quite a large shift, especially on the heat side, of much more extreme hot weather and a sort of a new kind of hot weather. Warmer air also means less frequent but more intense precipitation. So for example, on a cold winter's day, if you walk into a warm house, you'll often feel that that air is very dry. And that's because that cold air from outside has been warmed up, and now it's able to take up more water, exponentially more water, as a matter of fact. So all else equal, rain or precipitation occurs when a body of air is saturated with water. So you can think of it as, say, a bucket, or the capacity of a given body of air to hold water as a set volume, all else equal, like a bucket is a set volume. When that bucket becomes full, it dumps out or creates a precipitation event. If the body of air is warmed up, once again, all else equal, you've essentially created a bigger bucket. It's able to hold more water, so it takes longer for it to fill. And then once it is full, or once the capacity for it to hold water has been reached or saturated, there's now be more water that precipitates out. So that leads to both an increased likelihood of drought in some areas and an increased likelihood of intense precipitation. Looking to the past, we have already observed an increase in atmospheric moisture since the 1970s of about 4%. We've also observed an increase in very heavy precipitation events. In the part of the country where I live, by about 71%. In others, less, 5 to 37, 27, depending on where you live. We also expect some parts of the US and other parts of the world to experience more droughts. This is a slide showing a very extreme drought from 2012. And as I mentioned, in some parts of the country, especially the Southwest, we're expecting to see droughts become more prevalent and more intense. Okay, another key systems concept that I want to bring up is the concept of feedback loops. So here's an example from the climate. We've got an increase in temperature causing a decline in Arctic sea ice extent, melting of sea ice. If there's less sea ice, the surface is less white or less reflective, and so there's less radiation that goes back to space and more that's absorbed by the oceans, that leads to warming or an increase in temperature. So feedback loop is a situation where a change in one element in the system leads to subsequent changes that feed back to cause another change in that same initial element. So in this case, we've got what we call a reinforcing feedback loop, where an increase in temperature can lead to further increases in temperature through this feedback loop. And this is actually what's responsible for much of what's called Arctic amplification of warming. And the Arctic is indeed warming about 2 to 3 times faster than the global average. And I'll just bring in a little bit of my own work in microbial ecology, where we're looking at the process of methane production or methanogenesis in Arctic peatlands. And we were interested in how different types of peatlands responded to vegetation changes, climate changes, and responded through methane production. And so here we've got in one case a type of ecosystem which is low nutrient, dominated by sphagnum moss. And in this ecosystem, acetate accumulates and does not lead to the production of methane. And then another system, which is minerotrophic, or high nutrient, it's dominated by this sedge-like vegetation, and methane is produced from acetate in these systems. It doesn't accumulate, it just gets transformed into acetate. That's important because methane is a very powerful greenhouse gas. So a change in these ecosystems can lead to a change in climate. So here we've got CO2 emissions leading to global warming. That climate change is leading to shifts in temperature and also shifts in vegetation in the Arctic, and actually shifting more systems towards that high nutrient condition, stimulating the production of methane from acetate, leading to methane production, and then ultimately leading to more warming. And that's another example of a reinforcing loop. So leading to basically an exponential increase in methane from those sources over time. So these types of feedback loops can lead to another key system feature, which is nonlinear behavior. So one example of nonlinear behavior is exponential growth. Another can be abrupt or threshold kind of behavior. So here we've got an image of surface melt of ice in Greenland here on July 8th in 2012. 4 days later, July 12th, going from something that looks pretty normal, about 40% surface melt in the summer, to roughly 97%, something that was very rapid. Okay, and a last system concept that's really critical in thinking about climate change is that of time delays. And this is really just a kind of cartoon animation to show you how stocks and accumulation in stocks can lead to delays in systems. So at the top of the slide, what you see is that first one that we started out with, that first jar. CO2 emissions leading to an increase in atmospheric CO2 because they're greater than removals. Other examples of stock and flow systems in the climate are the energy balance, so incoming energy leading to changes in global temperature. And in this case, what we've got is atmospheric CO2 basically causing a decrease in the amount of energy that's escaping to space. And then, of course, global temperature also influencing the melting of land-based ice to influence the volume of the oceans. So one way to visualize that, then, is to see atmospheric CO2 builds up and then ultimately causes a shift in temperature and a volume of oceans, but with a delay. I'd invite you to explore these dynamics for yourself. And here's an example of the climate momentum simulator. And you can see how changing emissions leads to changes in atmospheric CO2, changes in temperature, and also changes in sea level rise over time. You can see that it takes a long time for sea level rise to respond to the changes in emissions. Okay, so I want to start wrapping up by thinking about what some of our choices are looking out to the future. So here you see global surface warming from 1900 to 2000, and then out from 2000 to 2100. And some of the impacts that we're facing, depending on the trajectory, you see different possible trajectories that we might follow from here to 2100. So one is locking in ice sheet melt, and with that, the potential for multi-meter sea level rise. Another is extinction of plant and animal species from climate change alone. So that's something that we start to see further out and that we could avoid with a lower emission scenario. Also is the possibility of rapid sea level rise within decades if we really push on a high emission scenario. And I also want to point out that we could take action and we could reduce our emissions substantially. And if we do that, remember that we need to think about the scale of action. It's too late for 2011 to be a peak emissions year, but here if we look at other possible emissions trajectories to meet a 2-degree goal, a goal of limiting warming to 2 degrees above pre-industrial times, these are some examples of emissions trajectories that are commensurate with that goal. So either way, we're talking about substantial change. And an invitation to you that whatever your interest in biology, it's likely to play a key role in climate change moving into the future, in understanding and projecting biological impacts, in adapting to climate change changes that are now inevitable, some of them, in developing new technologies to reduce fossil fuel emissions and to sequester greenhouse gases, to improve public health and make our systems more resilient to a changing climate, and to educating and communicating with others, so hopefully we can address this problem effectively.